I want to now talk about some exceptions to the rule. So we've followed all the rules for drawing Lewis structures, and there's a couple of times when things are not going to follow all the rules completely. The first kind that we're going to talk about is something called a free radical. A free radical is when you have a single unpaired electron in your molecule, okay? So in place of where there normally would be a lone pair, you just have a lone electron. Free radicals are very reactive. You have a whole system in your body for taking care of them. There's enzymes that go around and clean them up, and that's because they are very reactive and they'll react with anything they find, like your DNA or proteins in your cell. Okay, I'm going to draw one free radical for you. This is NO2. I'm going to put my N here. I'm going to put my O's on the outside. I should have 5 electrons from N, 12 electrons from O, so that's going to give me 17 electrons. I've put 4 in my structure, so I'll fill in the rest. 6, 8, 10, 12, 14, 16. Now I have 1 electron left, and I can't put it on the oxygens because they already have their octets complete. So I'm going to put it on the nitrogen. And I don't have another electron, so this is all I've got to work with. Now my nitrogen doesn't have an octet. It only has 5 electrons right now. So I'm going to go ahead and erase a couple of electrons from this oxygen on the right and draw my double bond between nitrogen and oxygen. And now nitrogen has 7 electrons. So you might be thinking, gosh, I should try to share more electrons. But if I were to do something like erase these 2 electrons on oxygen and draw the bond, how many electrons does nitrogen have now? It has 9. And 9 is too many. Nitrogen has no ability to go beyond 8. And so that is not the right thing to do, and we're going to draw those 2 electrons right there. So this molecule, even though my nitrogen doesn't have an octet, it's a free radical, and we're going to call it good because it can't have 9, so 7 is as many as it can have. The last thing I want to do here is just do some formal charges. This oxygen will be -1 and nitrogen will be +1. Again, that's comparing how many electrons they brought to the table versus how many they have now. Nitrogen should have 5 valence electrons. It only has 4 in this molecule, and so it's a +1 formal charge. Oxygen should have 6, it has 7, and so that makes it a -1 formal charge. So that's the first example, which is a free radical. The second example that we're going to talk about is when you have a reduced octet. So this can happen when you have something like BF3. And boron only has 3 valence electrons. So it generally only makes 3 bonds, but let's draw our Lewis structure following our rules just like we normally would. We've put in our sort of skeletal structure here. Boron's going to give us 3 valence electrons. We're going to get 21 more from fluorine, so we'll have 24 electrons total. I've used 6 electrons. I'm going to fill in my octets on the fluorine. So that's 8, 10, 12, 14, 16, 18, 20, 22, 24. And I don't have any more electrons, so I can't put them on the boron. Now, normally we would say, oh, this is a problem because our boron here does not have an octet. But let's play devil's advocate and let's say we want to make a double bond because we're following all of our rules. So I'm going to erase these electrons from fluorine and I'm going to draw a double bond here and make it share those electrons. So now let's look at our formal charge. Everybody does have an octet, but my fluorine here is going to have a positive formal charge and my boron is going to have a negative formal charge. It only had 3 electrons and now it has 4. Fluorine had 7 and now it has 6 in this structure. So this is actually very bad. So we learned in our principles for drawing good Lewis structures that we want to maximize bonding and minimize formal charge. But this is a situation where when we maximize the bonding, we're increasing the formal charge. And that's the situation where we choose not to do that. So in other words, we're reducing formal charge as our priority here, not maximizing bonding. So I'm going to erase this stuff that I did here with our extra bond and go back to our structure with fluorine. Here we have no formal charges in this structure, and everything is more stable that way. So our two principles are maximize bonding and minimize formal charge. But if we have to choose, we choose minimizing formal charge. Okay, the next one that we have is an expanded octet. We can have expanded octets for elements that are in the third period on the periodic table or below. And that's because they have access to d orbitals, which means they have more creative ways that they can arrange their electrons. We're going to draw an example, BRF3. So BRF3, I'm going to put my bromine in the middle, and I'm going to draw my fluorine atoms. I should get 7 electrons from bromine and 21 electrons from fluorine, which is 28 electrons total. I've used 6, so I've got 2, 4, 6. That's 8, 10, 12, 14, 16, 18, 20, 22, 24. But I have a little bit of a problem because right now I have 4 more electrons. I can't put them on the fluorines. They're actually going to end up going on bromine. So bromine in this instance has an expanded octet and has a total of 2, 4, 6, 8, 10 valence electrons in this molecule. That's okay. It can go up to 12 when it's using an expanded octet. So that's an example of having an expanded octet. So the last thing that I want to talk about again is that our rules for this are to maximize bonding, but in particular maximize bonding when it reduces formal charge. If we maximize bonding and it increases the formal charge, then we don't do that. So we're prioritizing reducing the formal charge here. I'm going to do one more example, and this is sulfate. Sulfate is a little bit controversial, but we're going to do it anyway. So SO4 2- is the formula for sulfate, and I'm going to draw that framework and count up my electrons. So I should have 6 plus 4 times 6, and then plus 2 extras, so that'll be 32 electrons. I've used 8 of them, so I'm going to fill in the rest. That'll be 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I feel pretty good about this structure, but I know this is an ion, so I'm going to assign some formal charges. And what I'll discover is that I have negative formal charges on all of these oxygens, and I have a plus 2 formal charge on the sulfur. Plus 2 formal charges or minus 2 formal charges are pretty uncommon. We generally don't see them, and in this molecule, the way we've drawn it right now, every atom has a formal charge, and that's generally not good. So we're going to try to minimize the formal charge, and in this case for sulfur, it means that we'll have to expand the octet. So what I'm going to do is I'm going to erase 2 electrons from this oxygen on the right, and I'm going to draw the double bond between sulfur and oxygen. Now that is adjusting our formal charges. My oxygen now has no formal charge, and my sulfur is going to be a plus 1 formal charge. So I made an improvement there, feeling pretty good about it, but I still have formal charges on 4 of these atoms. So I'm going to see if I can make another double bond. So I'm going to erase 2 electrons over here on the left, draw my double bond. Again, this helps get rid of that -1 and now the +1 on the sulfur, So we only have 2 atoms that have formal charges in this ion that has 2 charges, and so that seems reasonable. I want to point out a couple of things about this. So first of all, notice that sulfur now has 12 total electrons in its valence. That's kind of the maximum that we can do. Even when we're expanding the octet, we don't really go beyond 12. Another thing I want to show you here is we might be tempted because we still do have those formal charges on the oxygen. So we might think, I'm going to try making another double bond. So I'm going to do that here. I'm going to erase those top electrons, make this double bond, and then we're going to reevaluate. It turns out now, if I count it up for sulfur, now my negative formal charge would be on sulfur. And even though I've made more bonds, which is generally good, now I had to move my formal charge from oxygen, where that's a pretty electronegative element, to sulfur that's much less electronegative than oxygen. And so that is a bad move. So this is bad for 2 reasons. The first is it would give sulfur 14 electrons, which is just too many. Even in an expanded octet, we're pretty limited to about 12. And the other thing is that we've moved the formal charge, the negative formal charge, from an electronegative atom to a less electronegative atom. So that is no good. So I'm going to undo what I did there, put these electrons back on oxygen where they belong, and this will be my final Lewis dot structure for sulfate. Again, principles here: maximize the bonding when it reduces formal charge, and if you have a choice between structures that have negative formal charges on electronegative atoms and negative formal charges on less electronegative atoms, you always want to put the negative charge on the more electronegative atom. That's going to be better able to deal with the extra negative charge. Okay, that is the summary for Lewis structures. Thank you for listening. I hope it was helpful, and I hope you have a great day.